Iceberg! Iceberg up ahead! Iceberg! Iceberg!
What's that noise?
I think Oliver's reenacting his favorite scene from the Titanic again.
Oh jeez, I guess we better go check on him then.
Iceberg! Iceberg!
Something's wrong with my iceberg, guys. Out of water, the thing looks like plenty to crush my Titanic. But in the tub, it's like the whole thing's stuck under the surface.
You do realize that most of any chunk of ice will be mostly underwater, right?
What?
Yeah, I mean, it's not like that ice cube's just gonna sit on top of the water like it would on a countertop.
Yeah, I do wonder what percentage of the ice will actually float above the water.
Well, I think some simple Unit F physics will help us get to the bottom of this.
Let's do it!
You get drying off, we'll get started on the equations.
As we have seen, an object floats when its weight is equal to the weight of the fluid it displaces. Let's use this condition to determine just how much of a floating object is submerged. We will then apply our result to the classic case of an iceberg. It is important to note that the force of buoyancy is essentially an object's weight, as the two must equal 0 for an object to stay afloat. Consider then a solid density, d of s, floating in a fluid of density, d of f. The solid has a volume v of s. Its total weight is the weight of s equals the d of s times volume of s times gravity. Similarly, the weight of a volume v of f of a displaced fluid is equal to the weight of f equals the density of f times the volume of f times gravity. Equating these weights, we find the following. The density of s times volume of s times gravity equals the density of f times volume of f times gravity. Canceling g and solving for the volume of displaced fluid, we have v of f equals v of s times density of s divided by density of a fluid. Since, by definition, the volume of displaced fluid, v of f, is the same as the volume of the solid that is submerged, v of sub, we find submerged volume, v sub, for a solid volume, v of s, and density, d of s. Floating in a fluid of density, d of f. We now apply this result to ice floating in water.
So what percentage of a floating chunk of ice projects above the level of the water? Assume a density of 917 kilograms per meter cubed for the ice and 1,000 kilograms per meter cubed for the water. These two values are taken right from the book. In the case of a chunk of ice floating in a glass of water, the solid object is ice with a density d of s equals d of ice, which is equal to 917 kilograms meters cubed. And the fluid of water with a density d of f equals d of water equals 1,000 kilograms per meter cubed. We can apply Ben's equation to this system. First, the fraction of the total volume of ice, v of s, that is submerged is v sub over v of s equals d of s over d of f. Hence, the fraction that is above the water is just 1 minus d of s over d of f. Multiplying this fraction by 100 yields the percentage above water. Calculate the fraction of the total volume of ice that is submerged. V sub over v of s equals 0.917. Calculate the fraction of the ice that is above water. 1 minus 0.917, which is equal to 0.083. Multiply 100 to obtain the percentage. 100 multiplied by 0.083, which is equal to 8.3%. Because we seek a percentage, it is not necessary to know the total volume of the ice. Thus, our result is that 8.3% of the ice is above the water, applies whether we are talking about an ice cube in a drinking glass or an iceberg floating in a freshwater lake. If an iceberg floats in the ocean, however, it will float higher due to the higher density of seawater. We consider this case in the same fashion as it is with the freshwater. The density of seawater is equal to 1,025 kilograms per meters cubed. All we have to do is plug that into the previous equation to get 0.895. Subtract it from 1 and multiply by 100, which yields us with a 10.5% of the iceberg that floats above the water.
So, does all that science really add up? Well, I've put together an experiment to test the theory that ice will actually float higher in a more dense saltwater solution than it will in a freshwater solution. I'm doing so with a couple rubber bands, a glass of salt water, a glass of fresh water, and 2 ice cubes, about the same size. I use this rubber band to mark the height that the ice cube should reach when it is placed in the fresh water. And you see with my saltwater glass that I have the same amount of fluid and that the rubber band is placed in the exact same spot. Now, the difference between these 2 ice cubes, if this were a glass of fresh water and this a glass of seawater, would only be 2.2%. To exaggerate the effect of a more dense liquid, we decided to add a little bit more salt than would typically be found in the ocean. Now I'm going to put my ice cube inside the freshwater glass. You should see the ice rise just to the rubber band mark. Next, I'll place my ice cube in the saltwater glass. Observe as the ice actually floats above this rubber band mark. My God, I think that actually worked. So there you have it. While the difference in heights was admittedly subtle, ice certainly does float higher when it is submerged in salt water than it does when it is submerged in fresh water. Just a little simple physics. I won't let go, Jack. I won't.
So in the end, the iceberg that took down the Titanic was almost 90% underwater.
That's right. So even in a freshwater tub, you need a much larger piece of ice to crush your toy.
Iceberg! Iceberg up ahead! Iceberg!